All right, guys, here we go. Last topic for today. This topic is logical equivalence. And we'll also use the idea of logical equivalences to help us figure out some negations. Okay, so what is a logical equivalence? A logical equivalence, which we denote with this double arrow, what do you call it? Double arrow? It looks like the biconditional arrow, except if you look at it, it's doubled up, yeah? That's the symbol for logical equivalence. And what the logical equivalence symbol represents, it basically represents the equal sign. Now, we don't use equal signs between statements. So instead, we use this symbol right here. Yeah, it means that two statements are essentially the same. They might have a different appearance, but they're logically equivalent. Now, what gives us a logical equivalence? We get a logical equivalence when we start a statement with a biconditional, and then we find out that this biconditional statement is a tautology. It's a tautology. So here's basically what happens, right? I have like some statement. It could be a compound statement on the left, and then I have some other statement on the right. And then when I end up putting their whole truth table together, I look at that column, P if and only if Q, I see that the last column, that column is all truths. There would never be a case where there's 6 rows because it's always the power of 2. But anyway, yeah. So if I'm looking at this P if and only if Q as a truth table, and no matter what the individual components of the statements is always true, then that makes it a tautology. And if it's a biconditional statement, we call it a logical equivalence. Now let's look at these 3 examples of proving logical equivalences, 7, 8, and 9. And then we'll use that to talk about negations next. So here I wrote the questions down. Try them on your own first. How do I go about proving that something is logically equivalent? Well, here's the strategy. The strategy to prove logical equivalence is to show that the original statements as a biconditional statement is a tautology. Now, if I can accomplish this task, then that means I prove the logical equivalence. Right? So right now it's only a regular biconditional. Once I prove it's a tautology, then I can say, oh, that was verified. That was right. So how do I do that? Let's do that statement. I know I only have a P and a Q. That means when I go and do my truth table, I'm going to need 8. Not square. I'm going to need, not 8. I'm sorry. I'm going to need 4 rows, yeah? Following the convention that we learned in the last class. Okay, so I need to build this whole thing. Looking at the left side, I need a if P then Q. Looking at the right side, I need a P and not Q. So I'm going to need a not Q. Okay. I'm also going to need a if P then Q. That's this part. And then I'm going to need to negate that. So I'm going to do the negation of if P then Q. Notice the parentheses means this if then happens first. Okay, I have to squeeze this thing in. Okay, now I can build the right side P and not Q. And then that's so I have the left side, I have the right side. Last thing is to put it all together. And, shucks. I'm not sure if this is going to work, but, oh yeah, it works. Move it over a little bit. So my very last column is going to be this whole thing together. I'm just going to write it in 2 layers at the right side of this box. So I'm going to squeeze it in here. Okay, what is it I'm squeezing here, though? It's just the original conditional statement. Because I'm trying to show that it's that original conditional biconditional statement, is a tautology. And if I do that, then that means I've successfully completed my task of proving the logical equivalence. So again, just to reiterate, to prove a logical equivalence, what do? You show that you have a tautology when you have the regular biconditional statement. I just threw a lot of language at you just now with that statement I said. So let me say that one more time. To prove a logical equivalence, you want to show that the biconditional is a tautology. So we used 3 vocab words just now. And if that made sense to you, that's awesome. That means you're learning the language of math. And if it didn't make sense to you, then rewind and listen again until it does make sense to you. Okay, here's the standard star right, not Q. We've done that before. Just a reversal of the original Q. It's false, true, false, true. If P, then Q is also something we've seen before. We're only false when we start off true and then false here. We're in the second row. Negation of that, it'll be the opposite of this column right there. Make sure you guys are able to reproduce this table completely by yourself. Now I'm looking for P and not Q. That means this and that column. So the first and third column with an and in between. And in between means where are they both true? That's where it's going to be true. Right there in that second row. And that's the only time it happens. So the rest is false. And now comparing the two, you note that they're the same, right? So when I combine them with the if and only if statement, they're always matching, which means that I always get trues for the biconditional, and therefore it's a tautology, and therefore we've proven that we have a logical equivalence there. Okay, number 8 is the same thing. I'm just gonna, I'm gonna jump through it. You guys should do the same. There we go. Again, I only have 2 letters, which means, again, I have only 4 columns. I got P, I've got Q. Let's do the not P. I like to do the nots if I have individual nots first. This is just preference. Eventually, as long as I only do one thing at a time and eventually I build towards these 2 final statements, actually this final statement, then it's okay. I'm going to do P or Q next so that I can take one more step to negate it and get not P or Q. Then I'll have the not P and not Q. So that's the right side, and then I can put it all together then. So let's see, that's a not P or Q, if and only if not P and not Q. All right. And the rest of the table almost fills itself out. There's really only one way to do that now. Just follow the rules, right? Follow the rules, starting with the first 2 columns the standard way. And what I mean by standard way, I mean since there are 4 rows, I'm going to do true, true, false, false for that P, and then true, false for the Q. All right, so true, true, false, false, and then true, false. The standard start for 4 rows. Not P is the opposite of the original P. Not Q is the opposite of the original Q. Or something we see many times before. True as long as one or the other is true and false otherwise. And then the negation of that is going to be in reverse. So instead of true, 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 false, it's going to be false, 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 true. Now I have the negation of P and negation Q. That means I'm focusing in on these 2 columns. Connecting them is the and, which means I'm looking for where they're both true, and they're both true only at the bottom. So that's where it's true. And notice, again, I have this matching happening. So when I connect those 2 with a biconditional, it's going to be always true. And so I've proven a tautology. If this is a tautology, then that means this logical equivalence is accurate. So I've proven that logical equivalence. Okay, one more similar type. And number 9, you notice is almost the same as number 8, really. Super similar, except that the symbols are just switched, yeah? And if you're looking carefully, that should also look familiar to you. We'll talk about that in a little bit, but maybe you can figure out what that looks like to you. Okay, same idea here. Put the negations again. And then let me do P and Q so that I can do not P and Q. Those should be 2 separate steps. Here I have not P or not Q. That's the right side, yeah. and then I put the whole thing together. So not P and Q, if and only if not P or not Q. All right. Okay, let's fill this thing out the usual way. Oh man, my line went just a little over the line. Oh, that line is. Boxes are not the same size, but whatever. Okay, usual start. Not gonna say much more about that. That's a F right there. Not P is the reverse of the original P. Not Q is the reverse of the original Q. Q. And then P and Q, something we've seen before. It's true when they're both true. False otherwise when there's a false somewhere. So that's going to be true, false, false, false. And then the reverse of that is going to be false, true, true, true. Now I've got not P, not Q. Those two guys, right? Combining them with an or. Or means as long as one or the other is true. And the top, they're both false. So that's at one time it's false. And otherwise, it's true at least in one spot. So that's true, true, true. Now combine those two statements. Here's the left. Here's the right with a conditional arrow. Conditional means as long as they match up, then it's true. And they always match up. So again, I have a tautology. Awesome. So proving this conditional statement is a tautology means that I do have a bicondition. I'm sorry, I do have a logical equivalence. All right, let's take a pause here. Actually, maybe even pause for yourself before you continue on. Give your brain a little break. So pause for 30 seconds, and then let's come back. We're looking here at the result of what we just done. So if you look at number 789, 789. Okay, look carefully at what we've shown. What did we show? Let's start with number 7. So here I have a statement, right? If P, then Q. And then on the left of that, there's this negation sign. So what I'm looking at is the negation of this statement here. What is that equivalent to? Well, it's equivalent to this statement. I've just shown that it's equivalent to that statement, right? I've proven it by showing that truth table is a tautology. So what does it all mean? That means if I want to negate a conditional statement, if P then Q, then how can I go about that? I can go about it by writing this statement right here, P and not Q. And so it turns out P and not Q is the standard way to negate a if P then Q statement. And let that sink in. Pause the video if you need to think about that. If I negate an if then statement, negating that if then statement, the result is a P and not Q. So the pattern is you keep the left the same, negate the right, and you switch this conditional to an and. That's how you negate an if then statement. So let's look at this table now. The original statement is if P then Q. I kept the left the same, negated the right side, and transferred this and in between. Let's use a different color for that. I'm sorry, transfer this if then statement, to an and. That's how you negate. Okay. And then there's another important negation. And that is, if I start off with an or statement, and I want to negate that, well, it's kind of like it almost distributes. It's almost like this distributive property, right? This negation distributes to each individual side, and then that middle flips, where it wasn't or to begin with, becomes an and. Let's talk about that one more time. So I got P or Q, right? Switch to a not P and a not Q, and then reverse the middle. Or if it started off as an and, reverses to an or. P became not P, Q became not Q. Doesn't that look familiar to you? That should look familiar to you. This part right here, these two statements, these together are called De Morgan's laws. And this is, since we're talking about logic, this is De Morgan's laws for logic. Okay, just recall, what were De Morgan's laws for sets? So recall. For sets, we had, let's use P's and Q's for sets just so we can see the parallel more clearly. If I had P or Q as a set, and I wanted to negate that, I would take the complement, right? The complement of that, remember, was equal to negating each individual side and reverse that center from an or to an and. Or the other half of De Morgan's laws was if I started with an and I want to negate that, I would split that negation to either side and switch to a union. Now compare this here to that there and see that it's basically the same, right? If I convert my symbols from set theory to logic, it's really the same. That's why they're both called De Morgan's laws. This one on the right was De Morgan's laws as well, but for sets. That looks like sets. That was a T. Sets. All right, guys. So almost there. Last few questions are just to apply what's here in this table. So if you look at this table, it tells us how to negate things, right? So we're just applying this. All right, let's do number 10. And let's translate this. Right now it's written in English. Let's translate it to symbols so we can translate it back to English at the end. If I do math, then I'm cool. That would be like saying if M, then C, right? That's the original statement. Or if you like, you can use P's and Q's. If M, then C, the negation. So right now we're practicing negations. The answer is the negations. Negation would be to keep the left the same, change the if then to an and negate the right. So this is the form of my answer. I'm going to translate now back to English for my final version since the question was given in English. So what's the negation? M was I do math. And is and. And negation is negation. I'm not cool. So this is the original. If I do math, then I'm cool. The negation says I do math and I'm not cool. That's the statement with the opposite meaning. Isn't that crazy? So that's the standard way we negate if-then statements. Okay, number 11. Number 12. We're going to apply De Morgan's laws for this one. So what is De Morgan's laws? Use a different color here. De Morgan's law says, if I have an or statement and I want to negate it, then I'm going to negate either side. So the not P becomes a regular P. The not Q becomes a regular Q. And just flip the middle. So the or becomes an and. And that's my answer already. Okay, one more practice. If I have an and statement, De Morgan's law says, negate either side. So not P becomes a regular P. Q becomes a not Q. And swap the middle. If it was an and, this time it's going to be an or. So that's my answer. Okay, number 13. I've got an if-then statement. We learned right here at the top, if-then statement to negate it. What is the pattern? Keep the left the same. Switch the if-then to an and then I'm going to negate the right. Negation of the right is going to be a regular old Q because I started off with a not Q. So P and Q is the negation there. Okay, number 14, you're a monkey or a donkey. Let's do the translation to symbols first. That says monkey or donkey. So the negation would be negation M and negation D, right? So now let's translate that back to English. Since the question was in English, you are not a monkey. And you're not a donkey, or just say and not a donkey. If you think about that long enough, you realize, yeah, that's true. That is the statement with the opposite meaning, the negation of the original. Okay, one more question. Number 15. If x minus 5 equals to 2, let's call this first part the P. Then x equal to 7. We'll call that part the Q, that statement the Q. So the negation then, what's the negation? I have an if-then statement. Pattern for negating an if-then is to keep the left the same. Change the if-then part to an and instead. And then change the right-hand side to its negation. So I end up with P and not Q. Right? Standard way to negate a conditional statement. And then lastly, let's translate this back into the language that it was given in. So originally it was given in sort of this math equation language, right? So how would I translate P and not Q? I would say x minus 5 is equal to 2. And x is not equal to 7. That's the negation Q, right? So that would be the negation right there. And just like that, guys, we are finished. Forgot to circle the answers here. Oh, I'm sorry. Actually, the actual answer was just this English part here. And same for this question. All right, real quick recap. What did we do today? We learned basically about the biconditional. That was the big new thing. Yeah. This new symbol. We learned it's true when they match up, false otherwise. We learned how to read the biconditional as if and only if. We also learned how to do translations back and forth. We learned that if a biconditional happens to be a tautology, then it has a special name. We call it a logical equivalence. And lastly, we showed that there's 3 standard negations. If I start off with an if-then, the pattern to negate is keep the left the same, switch to an and, change the right to its negation. And then I had the 2 other negations that come from what we call De Morgan's laws. And that's basically it. De Morgan's laws. All right, guys, have a great day. I will see you next time. Next class, we're finishing up chapter 3, and then we'll start preparing for the first exam. All right.